This is the lab video for Lab 16 pH indicators. This video covers parts A, B, and C. For a completed lab, you'll need to answer pre-lab questions 1, 2, and 3, collect the data and observations presented in this video, do any calculations required to complete the lab, and then answer reflective exercises 2, 3, 4, 5, and 6. If you are typing your answers and observations and calculations directly into a Word document, be sure that you are very organized and clear about your answers. You can save it as a Word document and upload it to the Lab Assignment 16 in Canvas. You can also write directly into your lab packet and then scan that document, save it as a PDF file, and upload it into the Lab 16 assignment in Canvas. Now, I would recommend before you start the lab to get your lab packet so you can have your procedure and data right there as you're going through this lab video with me. The other thing I would recommend is that before you even start any of it, that you go ahead and read the introduction so you have some background information for some of the words I'm using and for what we're talking about. If you'd like more background information, this lab corresponds to the chapter of acids and bases in your textbook. Before we get going, there's really two words that I want to make sure we all know. And one is just what is pH and what are we measuring? And pH is a measure of the acidity of a solution. It has a scale that goes from 0 to 14. So in the middle is 7, and that would be considered a neutral solution. And the numbers between 0 and 7, those would be an acidic solution. So for example, a pH of 5 is an acidic solution. And then between the numbers of 7 and 14, that would be considered a basic solution. So a pH of 12 would be considered a basic solution. So in today's lab, we're going to be measuring the acidity of several household products. And then we're also going to see how an antacid affects the acidity of a solution. And we'll be doing that by comparing the color of our solutions when they have an indicator in them to an indicator scale. And what a pH indicator is, it's a chemical that changes colors depending on the acidity. And we're going to be using a natural indicator that comes from the red cabbage. So when you boil red cabbage in water, the chemical, which is the indicator, is extracted into the water solution, and the water turns a purplish red color. When it's that purplish red color, that chemical can change color depending on the acidity of the solution. So we're going to be using a natural indicator. Hydrangeas also have a natural indicator. Hydrangeas are those beautiful, almost like pom-pom flowers that we see oftentimes in spring. They're sometimes associated with Easter, maybe Mother's Day, and they come in different colors. Well, those different colors can be enhanced or changed. The colors can be changed by the acidity in the soil because the hydrangeas have a chemical in them that will change color depending on the acidity of the soil. So it's kind of neat to think about. So let's go ahead and start the lab. And so part A, we're just preparing a scale that we're going to use to compare our solutions to for parts B and part C. So the first 5 steps were the directions of how to create the red cabbage indicator. Now, our lab manager has already made the solution for us. So if you would have done the lab, you would have come right in and the red cabbage solution would be prepared, which was the same for me. It was already prepared. So I did not do steps 1 through 5. So then with step 6, it says label 14 test tubes with pH values ranging 1 through 14. So here I was doing step 6. We only have up through pH of 13, so I only had 13 test tubes. And then step 7 said to each tube add 2 milliliters of a prepared buffered solution. So a buffered solution is a solution that contains what's called a weak acid and its conjugate base. And this mixture can be made for the solution to maintain or keep a specific pH. So we have a pH buffer of 1, and the solution of that solution always has a pH equal to 1. If I had a pH buffer solution that had a number 10, then that solution would always have a pH of 10. So we had 13 solutions, each with their own pH range from 1 to 13. And in the picture here, the first photograph right here, I had already put the 2 milliliters of the buffer solutions in each respective test tube. It might be hard to see because the buffer solutions are both clear and colorless. So then in step 8, I took red cabbage indicator, and I think in a future picture in the lab, I actually took a picture of the beaker that had red cabbage indicator. When it's in small quantities, it looks reddish, like a dark red, but when it's in large quantities, a lot of it looks purple. So I had added 2 milliliters to each one of these test tubes, and you can see it's a beautiful color. Looks like a rainbow. And so what we're going to record are the colors of these varying solutions, which have varying pHs. I've taken pictures of them closer on this slide. On the next slide, I took a photo also of all of them together closer. So that might also help you with the colors. So you're going to record the colors in part A here. Some of the colors look very similar. It's best if you can try to distinguish them, but if you can't, that's okay. It's particularly hard in photographs. It might have been a little easier in person. But you're going to record these colors, and I have them in order of pH. So I have 1 and 2. So all of the pHs up through 13. We did not have a pH buffer system of 14. So record the colors to the best of your ability, trying to distinguish between, you might say, hot pink or deep red, or whatever words that would help you remember what the color is. Now, a limitation of using a natural indicator, or really any indicator that's based on color, is that people's eyes aren't uniform when they see color. So if you're having trouble distinguishing, you may reach out to a classmate or a friend or someone else that can help you distinguish the colors. The most important thing is that even if you're not seeing the exact same color as someone else, we're trying to be able to distinguish and compare colors. So this is a limitation, and you do the best you can with it if you're limited by that. So on this slide, I have all the colors again next to each other. It is very pretty. This slide may also help you if you were having trouble distinguishing. It might help you see the differences, but you can see why a lot of people like this lab in terms of just what it looks like. So that would be part A. We're trying to set up a reference scale, something we can compare our other data to. So this is our reference scale. I did not throw it out till I was done with the lab. So now let's turn to part B, and we're going to use what we had from part A and part B. So step 1 said I would supply various household chemicals. And so here is step 1. I had ammonia, hand wash, a bathroom wash, a multi-cleaner, vinegar, rubbing alcohol, and Tide. When I have you collect the data, I will have each of those, so you don't need to rush and write them down now. And then to each test tube, this is step 2, I added 2 milliliters of the respective household substances. You may notice that I chose all clear and colorless solutions in anticipation that if I chose something with a strong color like orange juice or coffee, adding the indicator, the color change would be masked by that dark color. And so I was trying to choose things that were clear and colorless. This could be a limitation to using, again, this type of indicator. And so here are what my solutions look like. I did mix them, but the two that are foamy, the hand wash and the Tide, I tried to mix it, but the more I mixed it, the foamier it got. So when we try to match the colors, we'll look at the top layer of where the color is sitting. And so for part B, what you're trying to do is determine the pH of the household substance by comparing it to the scale we created in part A. Now your data also has a column for the pH measured by the digital meter. Currently our digital meters are not functioning very well, so I did not measure it with a digital meter. Digital meters have the advantage when they're calibrated and working well of giving you a decimal number, and so it is accurate, and when calibrated, very precise, or it's precise and very accurate. But when they're not working well, they are electronics, and so that's a disadvantage if they're not working well or if you don't have the solutions to calibrate them properly. And so what we're only doing the red cabbage, pH with red cabbage, and so you can leave the digital meter column blank. And so this is ammonia on the first one on the left. And then you would be looking, this is here's the numbers, the first test tube is 11 and 12. If you think something is in between, you could estimate a 0.5. So it could be like 9.5, 6.5. But we can't really get more precise than that. This second one is a method hand wash. Look at the color, not the colorless part at the bottom. And you can see here I have 5 and 6 in the first picture, and then I compared it to 7 as well. This is a method bathroom cleaner. So that's in this test tube, and then these are 6 and 7. Normally when I have time to prepare for this and I'm not in a hurry, we'll do things like carbonated drinks and stuff. This is a multi-surface cleaner. Looks like it's Mrs. Meyer brand. I'm a little surprised how neutral all of these are, all hovering around 5, 6, 7. Oftentimes soaps themselves are basic, but there's the 6 and 7. This is vinegar. That's the first test tube. And I chose 1 and 2 to compare it to. This is rubbing alcohol. And it's in the first test tube on the left on both examples. And again, I just have two. I chose first 5 and 6, and then I wanted to compare it to 7. And then this one is the Tide. It is a clear and free Tide. The colored Tide would be, again, kind of difficult. You can see how it would maybe mask the color. Now in this case, it's the one on the right that is the Tide. And so I compared it to 6, 7, and 8. I held them close there because the color was harder to see because of the foaming. And so this is part B, is just learning how to use, well, 2 things. It's kind of revealing about the pH of different things that are around us. And then the second thing is learning how to use a reference scale to determine information, like in this case, pH. And so then we have part C of this lab, and the part C is trying to determine how effective different antacids are. And so they had you obtain a single dose of 3 different commercial antacids and designate them as sample 1s and 2, and then record the mass of each of it. Now I, for whatever reason, did not take a picture of the masses, but I had recorded it. So the mass of the 1 dose, I think I'll write it on the next page instead of crowding it. So this is, we'll get to that. So don't worry, the mass of 1 dose I'll get to. This is Gaviscon, so that was one of the samples. And then the second sample I chose was Moorebrand. And the active ingredients were by tablet, so I did 1 tablet of each. The Gaviscon were much larger tablets. I don't think that will come across in the picture. And so they want you to record the active ingredients. So they want to know how many, how much, what it is, and how much. In your data page, it has a spot for 3. If we would have been in lab, I had 4 different antacids, but I only did 2. If this is hard to see, it's calcium carbonate. And again, it's per tablet. And it was 420 milligrams. I think the other one you can see. And so here, this is the Gaviscon. I did the Gaviscon first. And the mass of 1 dose, and I did 1 tablet because that's what the active ingredients were. You could take 2 to 4 tablets, I think. But the mass of 1 dose of the Gaviscon is 2.163 grams. So you're going to record that. And so I measured the mass of it. There's the tablet. I took a mortar and pestle, and I actually did several trials. I did 3 trials of it, but we're only going to measure 1. So you need to record the mass of 1 dose. And so then it tells me in the procedure to put it in a beaker, which you can see there's labeled. I put it from the all ground up into this beaker, and this number is a 7. It's hard to see with the glare. And this right here is the mass you're going to record, and it's the mass of the beaker plus the antacid sample. And so then started the process. I did 3 samples, so we're only looking at sample 1, but I was doing 3 samples to make sure it was all working out okay. So in the procedure, what it told me to do was it said that I need to take, and this is on step 6. I'm on step 6. It said take 3 milliliters of hydrochloric acid, and this is also step 6. There's a little beaker of the indicator. 3 milliliters of the hydrochloric acid and 2 milliliters of the indicator, and make your sample. And so we're only going to look at number 1. Like I said, I had done 3. But here, this right here is the acid and the indicator together after doing step 6. And then over here I have test tube with a pH equal to 7, because it's going to tell us to the test tube we want to add our antacid until we neutralize the acid in our test tube. So you can see the progression. If I were doing it, this is when I started. I'll just say I started at A, then I added a little, and they say just shake, but I gently mixed with a stirring rod. And then here I kept adding a little bit more. You can see the colors changing. This is the pH equals to 7. That's what I'm trying to match. Notice that it's not all dissolving in it. There's other things inside the antacid that are chalky. So there it's getting closer, and there it's getting closer. And then finally I thought, okay, this looks close enough to me. So what I did was I repeated the process of adding the antacid until the pH appeared to be neutral. And so then I reweighed the beaker, and here you can see I did 3 trials. And so I re-weighed it. You can see I used quite a bit of it. And so this is the mass of the beaker plus the unused sample. And so then you need to record this, because that's a part of your data. Okay. So now you should have collected, you have collected all the data for that. Now it says calculate the mass of the antacid used to neutralize. Okay, so if you take the mass of the beaker with the antacid that you started with and subtract this number, the mass of the beaker, and what is left, then you will have the mass of the antacid that was used to neutralize the HCl. And on the last slide, I will write that down. I just don't have room here. So now let's do the Moore brand. And I don't know if you can tell, but the Moore brand sample is the tablet is much smaller. So this is the Moore brand. And here we have, you're going to record. This is for the Moore brand, and this is the mass of the beaker plus the antacid. Oh, and before I forget, I did measure, even though I don't know why I didn't take a picture. I apologize. I had a lot going on. I measured, I wrote down, let me find it, the mass of the tablet. Okay, so here the mass of one dose, which I used as one tablet since that's what the active ingredients. The mass of one tablet is, I'm going to write it down here, this is 1.448 grams. So the mass of one tablet, and it says in your procedure, it says of one dose. So don't multiply it by 2 or anything. That was what I had as a dose. So that's the first column. So you have 2 things to record on this page: the mass of one dose and the beaker plus the antacid sample. And so I did it. I also did 3 samples of this to kind of go through. Here's where I added the HCl. And then I added, that was 3 milliliters of HCl. And then 2 milliliters of indicator, just like the other one. I set them up the same. And then I added antacid until it became neutral. So again, this is the More brand. And you can see I kept adding antacid and stirring and adding antacid. This one didn't look quite as chalky as the Gaviscon, and I don't know why, but it still wasn't clear like the pH of a 7. So I neutralized it all, and there you can see in this picture here I had all 3 samples I was working with. I guess I was being an overachiever that day. And so here, finally, you do need to record. This is the mass of the beaker plus the unused sample. And you can see I hardly had any left. I was glad it came to an end. So there was what I had left with the 2 different samples. Now in your data I mentioned that I would write it. So you recorded from the video the mass of one dose, the name and the quantity of the active ingredients, the mass of the beaker and the antacid sample, what you started with, and the mass of the beaker and what was left after it got neutralized. And so to figure out how much was used to neutralize, you will take the mass of the beaker plus the antacid sample. That's what we started with. And then you subtract the mass of the beaker plus the unused antacid. And so what you're measuring is how much I scooped out of the beaker in order to make the acid neutral to 7. And so when you subtract those 2 numbers, then you get the mass of the antacid used to neutralize HCl. And so then ultimately you're going to calculate the percent of a dose that it took to neutralize it. And we would think that the lower percent really means that it's more effective. So if it took less of the antacid to neutralize it, then that would be maybe an indication that that sample was very effective, at least at neutralizing acid. We aren't taking into account some of the other properties that maybe antacids help with. What we're looking at is how much does it take to neutralize the acid. All right, so remember, you need to answer pre-lab, do your data and calculations and reflective exercises, and then congratulations, you have completed all of the labs that you needed for this semester. Good work.